Hello everyone and welcome to this month's webinar by Sunwise on electrical theory for Solar 101. I want to thank everybody for joining us today. We have a lot to cover, so we're just going to go ahead and get right to it. And as always, this will be recorded and will be available on our website under our webinars within 24 hours. And please remember to ask any questions in the box. And Errol will be watching those for me and helping me out behind the scenes with those. Let's see, so with that said, let's go ahead and get started. My name is Rob Rallo. I have been in the off-grid solar industry for over 25 years now, and I actually have a bachelor's degree in electrical engineering. So I am an electrical engineer, and I got that from Villanova University, and I had to pull out the textbooks for this one, try to go back to some of those theories. And today's topic is going to try to show how that's going to apply to solar. So we're going to get into some detail on this, and so it might be a little bit boring, but if you bear with us, you will see how it applies to solar. And just like with any other type of course, it's going to build upon itself. So we're going to start with some simple stuff. We're going to see how we're going to build on that and build on that and build on that to get to some of the bigger and more complex stuff. Okay, just a quick background on Sunwise for those who may not know about Sunwise. Sunwise has been in the off-grid power systems business for over 20 years. Everything ranging from standalone solar to hybrids, battery backups, stuff like that. Let's see, we're an online retailer as well as systems integrator and design services company. We have our headquarters is in Oregon, but we have design and manufacturing offices throughout the country. Our other big warehouses in New York. As I mentioned, we do standalone solar. We can also do hybrid systems, cycle charge, battery backup, custom modules, component sales, pretty much anything to do with those materials. We do pre-assemble and pre-tester stuff. So when you get it, you know that it works. Some of the services, we can also do technical specification writing if you need to. We can do system design engineering for you. We can also do training, site survey, installation services, and things along those lines as well. So again, this is electrical theory for Solar 101, and what that does mean is there will be a 102, and so we're going to try to start with some of the basics. And again, if you try to bear with me through some of these things, you'll see how they do apply to you and why you should care about them, why you need to think about these things. So with that said, we're going to start with some of the simple stuff, just some basic definitions of energy, power, voltage, and current. And then from that, that's going to lead into resistance. Then we're going to go into Ohm's law. And then units matter. Something I was taught by a physics teacher back in high school that really kind of still applies today. And I'm going to go into that in detail on why units actually matter. And when you're doing your multiplications and divisions of these numbers of the energy, of the power, voltage, current, stuff like that, why it's important to also do the same thing to the units, to the watts, the amps, the volts, and all those things. So I'm going to show you examples of why that's important and why you should be doing that in order to make certain you get the correct number. Okay, then we're going to talk about AC versus DC. Actually, I'm going to focus on AC quite a bit. I know that most of our systems are DC based with the batteries and the solar arrays, everything else like that. But you may have an AC input either from a generator or from a utility source, or you may have an AC load. And it's very important to understand that, how that's going to affect the system and how that's going to work with it. So we're going to go into that in quite a bit of detail, actually, starting with single phase versus three phase versus split phase. Okay, there are differences there, subtle differences that make a big difference when specifying and ordering components, especially inverters or battery chargers, things like that. So we're going to go into that in detail. Frequency coming right out of that, and then power factor, which is another important one that most people kind of forget and ignore, but can cause you big troubles later on if you don't think about it or if you have a load that has a horrible power factor. Okay, then we're also going to get into, and again, we're covering a lot of stuff here. We're going to try to do our best to get through it in an hour. We're going to get into rectifiers versus power supplies versus battery chargers, and they are all each different, and they each have their own application, and you have to be very careful trying to use one for the other. So we're going to go into that in some detail. Inverters, we're going to talk about just some basic differences between a modified and a pure sine wave, but not going to get into that in too much detail, just some about that. And then DC converters, and then actually the voltage drop calculations, we're actually going to save that I think, for the Solar 102 webinar, which right now we have tentatively scheduled for January 24th. So again, that's going to go into that one because I think we're going to run out of time. Also on that one, we're going to go into more detail about how to read a schematic. So I'll be showing you some of the schematic symbols along the way for various things. So keep that in mind. We're going to apply that later on. And even a little bit today, you'll see how some of those build up, as I was talking about before, how they, hey, you learned it here, but geez, it's being used every year now. So again, these things build upon themselves. We're going to get into that in a little bit, and definitely more detail next time around. Talking about series parallel, wiring modules in series and parallel, and batteries in series and parallel, and things like that. So again, it's going to be a direct application of solar. Nodal analysis and loop analysis. Those are things used in electrical engineering that are really, what people don't understand, it's actually kind of funny. These are actually the basic principles of solar, especially when it comes to the battery. Nodal analysis is very important, and you probably use it every day in solar and don't even know it or realize it. So we'll get into that again on the Solar 102 webinar, but that's a neat one that I think people use every day and don't even realize where it comes from and why it works that way. So that's kind of a neat one. We'll get into that and the loop analysis on that one. Okay, so let's get right into the definitions then, starting with the current. And again, these definitions might be kind of a little big right now, but if you bear with me, you'll see how we can break these down into something a little simpler. So again, these definitions either came from an online search or straight out of my textbook from EE 101. Literally, that is a course, by the way, for electrical engineers, EE 101, and then second semester was EE 102. But anyway, so the definition for current, and again, the symbol for that is an A for amps, which I think we're all pretty familiar with, and is defined as the time rate of flow of electrical charge in the direction that a positive moving charge would take, and having magnitude equal to the quantity of charge per unit time. And again, it's kind of a big definition, but we'll break that down for you in just a minute. Voltage is kind of the same way. And again, we all know that symbol with a V, and sometimes followed with a DC for DC voltage or an AC for an AC voltage. We'll get into that in more detail when we get into AC versus DC. And it's defined as the electromotive force or potential difference between 2 points in a circuit as the difference in energy level of a unit positive charge located at each of the 2 points. And again, that's all pretty big. So what does that really mean? Well, basically, the current is simply the electrons flowing through the wire, or how much electricity is flowing through the wire. That's pretty much the current. And the voltage is that potential difference. And of course, the higher the voltage, the greater the potential. And you'll notice that little squiggly line is a symbol for a resistor, which we're going to talk about next. So resistance, which is represented as an omega, and it's because that's kind of a goofy symbol that not everybody may have on their computer. It's also just used with an R or ohm sometimes. And that's the property of a conductor by virtue of which the passage of current is opposed. So basically, it's literally just that. It's something that is resisting the flow of the electrons, resisting that flow of current. So it's a restriction is pretty much what that is that causes that problem. Now this is where we start to build upon what we said before. So resistance is equal to voltage divided by current. So that's R actually equals V divided by A. Or Ohm's law actually writes that as V equals IR. So voltage equals current times resistance. Okay, now, again, building upon that, power, which is shown as watts, W, is the energy transfer per unit of time. That's important to think about that. It's the energy transfer per unit of time. Okay, and that is the mathematical equation for that is P equals IV. So again, now we're going to build upon that again. And if you take that and break V down to Ohm's law as I times R, you can also define P equals I squared R. And what that means is you don't even have to know the voltage. All you have to know is the current and the resistance in the circuit, and you can figure out the power being consumed. So again, you can see how these formulas can kind of come in handy and they can play upon each other. Sometimes you don't have to have all the variables. All you have to have is one or two, and then using these formulas, you can find the other one. Ohm's law will be very important when we start talking about voltage drop, because that is the equation that is used to determine the voltage drop in a circuit. If you're working in a 12-volt system, voltage drop is a big problem. Again, we're going to table that conversation for EE 102, but it's going to come in very important there, so you're going to see Ohm's law come up time and time again with regards to that. Okay, there's a little symbol for that. Okay, energy. which watt hours is one of the common units for that. There are other ones as well, but that's the one that we commonly use in electricity. And you'll notice that energy is power over time. So it's pretty much, the formula is E equals, or energy equals power times time. So that's why you have watts times time, which is hours. It could also be watt seconds or watts minutes, but that's not normally how you think about it. When you get your electric bill for your monthly electric bill for the energy that you've consumed in your house, you get it in kilowatt hours. You don't get it as kilowatt seconds or kilowatt minutes. So again, watt hours is a more common unit for energy that we use here. It's important to understand that, again, it's power over time. So you can have the same amount of energy and you can have a high amount of power for a short amount of time, or a low amount of power for a long amount of time, and the energy is exactly the same. And that's important to think about when we're sizing solar power systems that comes to the battery storage and stuff like that, that what you're really trying to store is you're trying to store the energy, and you're not worried about necessarily the power. The power is important because, to an extent, that if you have a peak, you need to make certain that you can handle the peak with regards to circuit breakers or an inverter or something like that. But what you're really worried about when you're trying to size and design your system is the energy. So we're going to break that down a little bit further, but it's important to keep that in mind when you're doing your load calculations. You know, again, that energy, that you can have a high power load, but if it's for a short amount of time, that's okay. It's not going to make that system that huge versus having a smaller amount of power, but it's going to be over a long amount of time. Okay, so getting back to that again, as I said before, so energy is watt hours. It's literally watts times hours. Okay, and amp hours, which is what we use to talk about batteries and battery capacity, is the same thing. It is literally amps times hours. Okay, and watt hours per day, it's kind of the same thing. It's actually watt hours divided by days. Okay, and again, that's watt hours a day are kind of important when we're talking about load and power energy consumption there, and how big we're going to make a battery or a solar system or something like that. So these things are very important when it comes to sizing your system, and we'll go into these and figure out your load. And we're going to get into these again. Our next webinar next month is going to be on basic standalone PV system sizing. I know we had that one before, but we're going to do it again. And having the background of some of the webinars we've done over the last few months, ones like this one, it might help people kind of as a refresher and to understand how these principles then apply to how do you do your basic system sizing. If you haven't already signed up for that one, feel free to go to our website after this and sign up for it. Okay, so doing an example of how these units matter. So if we take 1 amp, let's say we have a 1 amp load at 12 volts, we multiply the amp times the 12 volts, and we're going to get 12 watts. Now, if we multiply that by 24 hours a day, we now have a load of 288 watt hours per day. Okay. Now, if we're looking for just the amp hours, then you can take that same 1 amp and multiply it by 24 volts, sorry, 24 hours per day, and you're going to get 24 amp hours per day. Keep that in mind. That is at 12 volts, though. Okay, and that sometimes comes. You can't forget that 12 volts sometimes when it comes around to making certain you have the right voltage for your battery. Now, along those same lines, if you have, say, a load of 500 watt hours a day, let's say somebody gives you, you're working on an off-grid cabin system or something like that, somebody gives you a load of, you know, hey, we know we're going to consume 500 watt hours per day because they've given you an electric bill or who knows what, and they want to take it off-grid. And that's going to be at 12 volts, then you can start working backwards with these things, and this is how the units matter. So you've got 500 watt hours per day, and there's 24 hours in a day, so then you can multiply these things out. Okay, so the days are going to cancel, and the days are going to cancel out, and the hours are going to cancel out, and apparently that did not work like it's supposed to, but the hours cancel out, and then you're just left with 500 watts divided by 24, which is going to give you 20.83 watts. Now, it's important to understand that is on average. You obviously might have a peak. You might have a, I don't know, well pump that might start up that might consume, I don't know, 150 watts, who knows what. You may have a peak load on there, but, you know, on average, you're going to have 20.83 watts, and you can use that to do your calculations for your sizing. Now, if you're, and if you again, since we're talking about this at 12 volts, if you divide that as watts by 12 volts, you know that on average, you're going to have 1.736 amps. And again, that's at 12 volts, that's on average. You may have a peak surge of, when something starts up, a pump, again, it might have a peak surge of 2 amps, who knows. So now, again, going back to some of those formulas, remembering that power equals current times voltage, or watts equals amps times volts, or watts divided by volts equals amps. We can then also figure out the amp hours per day from that. So if we go back around again, so if we take those same 50 watt hours per day divided by 12 volts, and again, your units can divide out of there. If you go all the way through with your units dividing out and canceling out, you end up with a load of 41.67 amp hours per day on average. And that's probably what you would use for sizing your system. Let's say you might want a 5-day autonomy for your solar power system. Well, you just take your 41.67, multiply it by 5 days, tells you how big your battery needs to be. So you can see how these units work together, and they help you to size your system. And again, we'll get into that in more detail. Next month, we talk about basics system sizing. But again, you can see how these things are important in the solar industry, and how these things build upon themselves, and how they work together to help you in designing and sizing and specifying your solar system. One of the things about electricity is you can't see it. I know it scares a lot of people and it confuses a lot of people. You can't see the electrons flowing in the wire. If you touch it, you can feel it, which is not recommended. I don't think anybody wants to do. You can get a nice shock off of that stuff. So you can kind of feel it. You don't want to, though, but it can happen accidentally. But you can't see it. So it's interesting that there's an analogy of electricity and water, and they're very similar in a lot of ways. So this is very common to talk about electricity in terms of water. And you can think of your current as being your flow rate, or the flow. So you can think of the flow of water through a pipe being the same as the flow of electrons through a wire. You can think of a battery there as kind of your pump. It's going to kick that voltage up. And you can see here you have an example of a standard 12-volt battery. So it's going to kick those electrons up from 0 volts up to 12 volts, acting like a pump going from low voltage to high voltage, or low pressure to high pressure. And you can think of your resistor kind of as a resistance or a restriction in that pipe that's going to restrict the flow of the water. So in this case, it's going to restrict the flow of the current. Okay, and even then, you can see there's actually an interesting principle with regards to water, where you have the flow is the delta of the P, which I think refers to power, divided by the resistance, which is kind of the same thing here. Ohm's law. It's current equals, again, the flow is the voltage divided by resistance. So what happens is your flow equals the pressure divided by resistance, whereas with regards to electricity, it's the current equals the voltage divided by resistance. So it's kind of the same thing. Again, the analogy is all the way through. So even though you can't see the electrons and see the electricity flowing through the wires, if you think of it in terms of the water analogy, it's amazing how well that works, and it really does apply pretty well all the way through electricity, including even some of the principles behind the formulas in it. Okay, so now let's jump into AC versus DC a little bit. So alternating current, which is usually used with shortened as just AC, is electrical current that reverses direction at regular intervals. We're going to get in those intervals a little bit further and talk about frequency. It has a magnitude that varies continuously in a sinusoidal manner. It's important to understand that is, again, usually it's defined with a sine wave. That magnitude does vary, and it's also the other important thing is it reverses direction, which basically means that AC, everyone thinks of as a positive number, but when you look at the waveform, it goes up and down. So there's actually, because of the sine wave, it is plus and minus across the 0 volts, and there's a crossing point there. And I'm going to get into that in just a minute when I show you some diagrams of this stuff. And direct current is which is shown as just DC, is electrical current of constant direction having a magnitude that does not vary or varies only slightly. And we say slightly because sometimes you may get, in the case of a battery, you have a range there that it may operate in, or you may have a little bit of a ripple on there. We'll talk about that a little bit more, coming from a battery charger or some other AC source. We'll talk about that a little bit more later. But generally, the thing to note here is it's always on the positive side. It never reverses itself, so it means it's never a negative value, okay, unless you're actually specifically working on a negative system. But whatever side of the line it's on, it's going to stay there. And also important to note that the schematic symbols for AC is a sine wave, and for DC, it's going to be a solid line with a couple of dashed lines underneath. And note those symbols. You're going to see those again a little bit later on. We start talking about inverters and DC-DC converters. So they're going to pop up there with regards to those symbols. And also, of course, in our next webinar, we talk about reading schematics. Also, schematic readings will be very important also in understanding nodal analysis and loop analysis. One of the reasons we're tabling that conversation to next week, to our next webinar as well. Okay, frequency. Okay, frequency is defined as the number of periods or regularly occurring events at any given kind and a unit of time, usually in 1 second. We're going to get into that in a second, how important that is in 1 second. Okay, so it's the number of cycles or completed alternations per unit time of a wave or oscillation. Interesting there is to talk about oscillation. One of the ways you can look at your waveform is with a device called an oscilloscope, which is actually measuring that. Sometimes you have problems with waveforms. You can hook an oscilloscope up to it and look at it and figure out what's going on. So that's kind of where that electrical tool comes from, the name for that. Okay, and the period is the duration, the time of one cycle and a repeating event. So the period is the reciprocal of the frequency. That's very important to understand. It's the reciprocal of the frequency, and we're going to talk about that in just a second. Okay, and these things are going to play out in a way that's going to make sense and it's going to matter as we go into it a little bit more detail here and talk about what that really means. So, since the frequency is the reciprocal or the inverse of time, okay, and the frequency is defined as hertz, okay. So if you were to invert that, you take 60 hertz, for instance, okay, and you invert it, then it actually comes out to 16.7 milliseconds. So that is the period of one cycle for a 60 hertz waveform, okay? Or if you're working with European voltages and frequencies, which is 50 hertz, it's 20 milliseconds. So you'll notice that there are less waves per unit of time for 50 hertz than there is 60 hertz because it's a longer duration wave. And that's important because if you're working with a lot of inverters have built into them transfer switches now. You've got inverter chargers and other inverters have transfer switches in them. Those transfer switches have a time delay to them. Okay, some of them may be around anywhere between, they could be as fast as 6 or 7 milliseconds and take as long as 50 milliseconds. Well, what that means is if you have something that's more in like the 10 to 11 millisecond range, it's pretty quick. That's what we call less than a cycle. Most loads, most AC loads can handle a blip of less than a cycle without it going offline. But if it's going to take as long as 50 milliseconds, that's going to be about 4 or 5 or more cycles. That's going to probably knock your load off. So if you're trying to use this as a UPS application, you don't want your load to go offline, you've got something that has a long delay on a transfer switch. That may not be good because odds are your load's going to go offline, kind of defeating the purpose of having having UPS system. So that's how this stuff matters. Again, so when you think about hertz, you can think of it in terms of time. You can think of it as, if you apply that to a transfer switch, you can see now how this might matter, understanding this stuff and whether that may be a problem for your load or not. Okay, so looking at these waveforms, and again, trying to understand that, we mentioned before that, 60 hertz is basically the same as 16.7 milliseconds, and 50 hertz is the same as 20 milliseconds. Well, if you look at this graph here, again, we're using the same voltage, so notice the amplitude or the height of the wave is the same, but you'll notice that the red wave is for 60 hertz, and it's going to end just a little bit past the 16, and the 50 hertz, which is the blue wave, is going to end at 20. So you can kind of get a little bit better picture of what's going on here, what that means. Again, notice that this is other neat thing to point out. We'll go into this in more detail in the EE102, is that this is a 460 volts AC or RMS, which stands for root mean square. We'll talk about that more in the next webinar. But what that means is that you'll notice that for 460 volts AC, your wave is actually over 600 volts, almost 700, and then it drops down going to almost minus 700. Well, when you actually talk about AC, you're not talking about the peak of the waveform. We're talking about something called root mean square, which is different. So when you start talking about 120, 240, you'll notice that your actual peak waves are actually higher than that. So it's just something to think about and consider. Again, we'll get in that more detail when we start talking about root mean square and more about those things in a different webinar. Don't want to go into that too much detail here. So we'll table that for another conversation. The other thing to note is that talked about reversing wave, and what that means is that you're crossing the 0 voltage point. So you'll notice you're going to go up, and then you're going to go down, you're going to go up, and you're going to go down. It's going to keep repeating itself. So you can get a wave that's going to go from essentially, a little over 600 volts to, a little more than minus 600 volts, okay, and back and forth in the case of 460 volts. A DC wave wouldn't be that way. A DC line is just going to be a flat line, whatever the voltage is pretty much. If it's 12 volts, it's going to be a flat line at 12 volts, which is a little variation for the tolerance of the battery for charging it. That's going to be about it. Okay, so just again, kind of a diagram of a sine wave, and I bring that up because there are other types of waves, and this applies to inverters. A sine wave might be nice and clean coming out of a generator or out of a utility power, something like that, but if it's generated by an electronic device, by an inverter, it may not look quite so clean like that. Okay, and we're gonna talk about that in a little more detail because that can really matter. So if you were to just take some transistors and chop your DC voltage, you can get something else like this A-square waveform, okay, which still has a frequency to it, by the way, in a period. So you can still think of this as being 50 or 60 hertz and still having that, still having it be 16.7 milliseconds. Okay, so just because it has a frequency to it doesn't mean it is a sine wave form. You can get a square wave, and you can even get a modified sine wave. So you might hear about a modified sine wave inverter. Well, this is pretty much what you got. You've got they go a little bit beyond a square wave. They can have greater steps to them, and they refer to that as a second order or fifth order. The more orders there are to it, basically a fifth order is basically like a 3-step or 3-level. Fifth order is like even more steps, and you can even go up to 7 and 8, 7 and 9. I think they work on odds. So you can get these steps to them, okay, but they're still not pure sine wave. They're modified, which means there's kind of an edge to them or sort of a sawtooth. And depending upon your load, that may or may not be a problem. If you've got a radio that is expecting a nice pure sine wave and you have some type of jagged waveform to it, that may cause some noise on your lines. There may be other devices that are expecting a pure sine wave that get kind of this square edge to it. That may cause your coils to heat up in your motor or something like that, and it may cause it to overheat or operate inefficiently. So I'm not saying that modified sine waves are bad. I'm just saying that you need to make certain that it's not a problem for your load, whatever your load may be. I would advise, if you're not certain, always just use a pure sine wave. That way there's never an issue. And actually, a pure sine wave actually starts out as a modified sine wave. And what they do is they just, again, they go to a higher order. They don't do a third or fifth. Sometimes they go as much as 7 or 9. And then they go ahead and run that through a filter to level out those edges to make it nice and smooth. Okay, and that's kind of what that last one shows. It's showing that being smoothed out a little bit. That's how they get their waveforms. Again, that's why you'll notice that the pure sine waves are usually a little bigger, a little heavier, a little more expensive than your modified, because they have to put inductors and capacitors and basically filtering parts in there to smooth out that wave, to smooth out those edges to get a nice smooth sine waveform to it. Okay, so we're going to continue on with the AC, and now we're going to talk about split phase, sometimes also known as single phase 3-wire. And again, that's the difference here. It's not single phase 2-wire, but single phase 3-wire. A single phase 2-wire would be more of a European style. Okay, it's also known as the Edison connection. That goes all the way back to when Edison started with electricity, because he would split or tap the transformers in the middle, which is how we kind of get it today. So you'll still hear that term used. I still use that frequently just because I learned that in electrical engineering school, but I think a lot of people refer to it more as a split phase, or even a single phase 3-wire is kind of a better way to think of it, because that's actually really what it is. It is a single phase with 3 wires to it. But if you look at a diagram, it's pretty easy to understand how that works. You'll notice that on the top side, basically this is the diagram of inverter, by the way. So keep this schematic symbol in your mind. If you got kind of the squiggly coil kind of idea on one side, and on the other side with 2 lines in between, that is a symbol for a transformer. You notice on the one side, that the top side, that is continuous. That's because that would be a 240 input, so to speak, or whatever the input voltage might be, and that's the 2-wire. So it's a 2-wire input to it. On the other side, you'll notice you've got a 240 volt, but it is a 120 240. You've got 120 on one side, 120 on the other, with a grounded tap in the middle. Well, that's your neutral wire. So this is how you get your three wires. You've got line one, you've got neutral, and you got line two. You can also think of it, look at the diagram on the right, kind of the same way. You've got 240 volts across the two 120 wires, but in the middle you've got this ground, this neutral tap. The other thing to note here is that these waveforms, going back to that sine waveform, they're inverted for each other. So this is the other thing that's a problem if you're only working with a two wire, because the two wire you only have one wave. But here on the 120/240, you've got the wave on the one side of the 120 is going to be inverted from the other. So they're what they call 120, they're 180 degrees out of phase. So they're completely out of phase from each other. And again, that could be a problem if your load isn't expecting that. So it's important to understand that there's a difference between a two-wire single phase and a three-wire. Normally in the US, you're going to most likely see the three-wire version, but it may come up depending upon whether you have a load that's tapping off of a three-phase, tapping a single phase off the three-phase, which can happen. We'll talk about that in just a minute as I talk about three-phase. So here we have three-phase. So three-phase is a symmetry of a three-phase system, basically power system, where each conductor is alternating current of the same frequency and amplitude. So in other words, it has the same frequency and it has the same voltage to it, the same amplitude to the waveform, so it has the same period and the same amplitude with reference to each other. But you'll notice that in three-phase, I remember I mentioned before that with the split phase, they're 180 degrees out. In this case, they're only a third out, so they're 120 degrees. So when you have three phases, you got 120, 120, 120, that gives you your 360 degrees for your full circle and full cycle. Okay. Now, this is the other thing that's important about three-phase. There are all different types of three-phase. If somebody has a three-phase load, that doesn't tell you everything you need to know. There's a lot of other information. The two basic configurations are basically a Y, which is actually shown as a Y, and a delta, shown as a delta symbol. Okay, the Y can be three-wire or four-wire. It kind of looks a bit like a star, and I'm going to show a diagram in just that in a minute. And it can sometimes have the middle of it grounded, and that gives you your four-wire, and that could be your neutral. You can't have that with the delta. Delta's never going to have a neutral. It's always going to be three-wire. Okay, and I'm going to show you the diagram that's going to explain that in just a second here. Note that both of these always have a ground wire. The ground wire is not connected to anything. It doesn't need to be. In the case of a Y, it could be connected to the neutral point, grounding it. But again, it doesn't have to. And that ground wire is always there, but it's always separate. So we don't think of that when we start talking about three-wire or four-wire. Same thing with regards to the single phase. We never talk about the ground wire because it's always assumed to be there. It isn't considered part of the actual flow of current because you should not have current flowing in a ground wire. So it's just there to ground stuff that should not have any current carrying in it. So again, we start talking about the number of wires in the system. The ground is always assumed to be there, but we don't add that into the numbers. We start talking about three-wire, four-wire, two-wire, etc. So here's the symbols representing that. So again, remember I mentioned on split phase you had line 1, neutral, and line 2. Okay, well you'll notice here with the Y configuration, you've got a line 1, a line 2, and a line 3. And where those three lines come together, you can have a point, okay? And that point can be grounded, giving you a neutral. Okay, it doesn't have to be there. Typically it is. It's actually pretty rare to find it not there, but it doesn't have to be. Okay, so that's how you get your four wires. Now the delta, you can see there is no place where those 3 points come together, so you can't get a neutral there. But you still have a line 1, a line 2, and a line 3. So just because you have three wires doesn't necessarily mean it's a Y or a delta. You're not always positive, so you need to find out. And different loads may want a delta configuration to a Y configuration. So it's important to know that and understand that. Most of your three-phase loads are going to be kind of big. They could be air conditioners, but generally they're going to be kind of a pump motor or some type of valve actuator or something like that. They're usually pretty massive when you start talking about three-phase. Okay, so just to continue on this briefly, we're going to finish up this three-phase on this one right here. You can also, the 208 delta can be kind of a formation of the 120Y. So when you start hearing somebody talk about a Y that's 120, 208, this is how you get it. You get 120 from line to neutral because there is a neutral and a Y. But if you go from line to line, you get the 208. So that's how you get it. Now notice that is not the same as the split phase, okay, which is going to give you 240 from line to line, okay? So that's the difference. So if you hear somebody, so somebody has the one, so 12208 is very different than a 12240. A 12240 is going to be that 3-wire split, single phase split phase, whereas a 12208 is always going to be a 3-phase, okay? Now, if you didn't have that line in the middle, then you'd end up with a 208 delta. And you can also have other variations on delta. You can have 240. You can even have 480 and the bigger stuff and things like that. Actually, I'm working on something now where the customer has a motor load of 460. Okay. Unfortunately, on the solar side, we don't have inverters that go that big in normal operation. So generally going to be working with these types of voltages with the inverters. These are your standard off-the-shelf models, and if you have to go higher than that, then generally what we do is we put a transformer on the output to kick it up to whatever the load needs, which is what I'm doing in the application I'm working on now. So I think that pretty much wraps up the 3-phase. Now from there, let's talk about the power factor, also staying in AC. And again, this one's going to be really important to understand, because what you start realizing is that and at the end of all of this, I'm going to get into inverters, and I'm doing all of this before we get to the inverters, because all of this applies to inverters. And it's very important to understand this with regards to the inverter and whether it's going to work for your load or not. Okay, so power is not the same. There's two different versions of power that comes to AC. If it's a DC load, it's completely different because there is no AC element to it. So when you multiply your volts times your amps, you're always going to get power. But what ends up happening with regards to AC is that because there are waveforms, and what can happen at power factor is your voltage waveform may not be exactly in phase or timed perfectly with your current waveform. If they were, then they would get your power, you would get your watts basically. That's your watts and that's your power. That's what they call real power. But unfortunately, sometimes in AC systems, there can be a lag, either with the voltage or the current in that waveform. And that lag is caused by an impedance in the load or some other type of impedance in the system. And impedance is usually a device that's not resistive. It's a device like an inductor or a capacitor. Basically, a motor has a bunch of coils in it, which is kind of a inductive type thing, which is why you hear about an inductive type motor, because generally there are coils in it. And that can create a lag in the current because you have to power up all these coils in a motor. Well, that lag between it and the voltage can give you a power factor that can adjust your system. Now, what you'll notice is that most motors actually have a capacitor on it, and that is to equalize that problem out of it so that you don't have a power loss associated with that lag. We're going to get in that in more detail and why it matters, how you can correct for it, or how you can deal with it. Okay. So again, the definition of power factor is the ratio of the real power flowing to the load to the apparent power in the circuit. So power factor, PF, is going to equal P divided by, which is the real power, divided by the AC voltage times the AC current. Okay? And that's the difference there is in those waveforms. Now, because you're going to notice that the volts, amps are going to cancel out, there are no units. It's always a number for -1 to 1. Generally, it's going to be in the 0 to 1 range. A negative would mean actually the circuit's giving energy back, which you do not want. That's how you can accidentally backfeed a generator and blow it up or something like that. So you generally don't want a negative number because that means something's being backfed, and that's not a good thing. So generally, it's between 0 and 1. Most loads are usually pretty efficient. You're going to find that in the 0.9, 0.95 range, maybe even something as low as a 0.8 or 0.85. That's generally not too bad. It's okay. It's actually rare unless you've got a pure resistive load of some form, say a resistive heater. You're not going to get a 1. Generally, there's always some type of little bit power factor there. But generally, if you've got a good, clean load, an efficient load, it's going to have a power factor that's still going to be pretty close to that 1 value. So again, defining the real power is the capacity of the circuit to perform work at a particular time, whereas the apparent power is the product of the current and the voltage. Okay, so again, it's coming back to this unit of time with regards to real power, with regards to the actual multiplication of the voltage and current with regards to the AC waveforms. Okay, so I already mentioned the impedance of the load. I just mentioned that they're not in phase. Let's see. Yeah, okay. That's going to get good enough. I already mentioned all of that. Okay. Yeah, I already mentioned all that. Okay. Okay, so now, how would this look in the waveform? This, again, comes back to the sine waveforms we already mentioned and getting back to some of this stuff. So, again, this stuff builds upon itself. You'll notice in the first one, you've got this, what we call unity power factor, which is basically 1, okay, which means there's no out of phase here. Your phase is 0, which means they're in phase, okay, and you'll notice that your voltage and your current waveforms line up on top of each other. Now, you'll notice in the next diagram there, your current is lagging your voltage. That's called an inductive circuit, okay, and that's a lagging power factor. Or if the voltage is lagging the current, it's referred to as a capacitive circuit or a leading power factor. And again, that just depends upon what's happening with the load. As I mentioned with the motors are very frequently have a lagging power factor. They're generally more of an inductive circuit. A capacitive type of circuit might be actually kind of a battery charging type of thing, to be honest. Something like that. Batteries, you got capacitors in it or something like that. So anything with a capacitive nature to it can cause that type of capacitive circuit or leading power factor to it. What type you have doesn't really necessarily matter that much. What you're worried about is how far off the waveforms are and what does that mean. Okay, so here's another diagram of ones that are completely out of phase with each other, giving you a power factor of 0, which is absolutely horrible. And another one that's just a little bit out of phase, which is giving you a power factor of 0.71. Okay, so what does this actually mean and why should I care? Well, what this means is that if you were to take a device that has a real power of 1 kilowatt, okay, but what ends up happening is because your voltage waveform and your current waveform on your AC system, on your AC load, are out of phase with each other. Okay, let's see, you have something that's really out of phase. Okay, that has a power factor, say 0.2. Okay, I know that's really a bad number, but it just kind of really drives the point home. You actually multiply your real power by your power factor, so you divide it by it. So you would divide that by that, and you could get, so in the case of the 1 kilowatt divided by 0.2 power factor, you're going to get an actual apparent power of 5 kVA. So the answer is, okay, so why do I care about that? Well, what that means is that the actual inverter or power supply device needs to be 5 times what you might think it is. Okay, so getting back to, I was saying we're to get into inverters. Well, this is how it applies to inverters. So if you look at an inverter data sheet, you notice the inverter data sheet isn't in watts. It's in volt amps. So if you had a load that you think is 1 kilowatt, you're going to say, hey, my 1500 watt inverter is going to be perfect for this, no problem. But what you didn't realize was it's a dirty load, it's not clean, and has a horrible power factor of 0.2, meaning it's really a 5 kVA or a 5,000 volt amp load on your inverter, but my inverter can really only do 1500 volt amps, which means this inverter can't support that load. So now that means all of a sudden your system's not going to work. So, like I said, sometimes you can see how this stuff applies. Thank you for bearing with me through all this stuff, but you can see why it matters and what it means. So you may be looking at inverter data sheets for years, not really understanding why it said volt amps and not watts. This is why it says volt amps and not watts. So it's important to keep that in mind. Again, if you've got a good load that has a power factor that's close to 1, it's not going to be an issue because when you're at 1, your volt amps equals your watts. They're exactly the same thing. But when you've got a power factor on there, it's not the same thing anytime you're off of that 1 mark, okay? Also note with this inverter, you'll notice that this is a 2-wire AC inverter, okay? So it has a range on the 120 side. You can do, say, 100, 110, 115, 120 volts AC. But on the 240 volt side, it could also do 200, 220, 230, 240 volts. That is a single phase 2-wire. That is a European style. So if you've got a load that's looking for 120, 240, this inverter will not work for you. So also keep that in mind as well when you're looking at an inverter spec sheet. Look at these things. Look at these numbers. Is it a 2-wire or a 3-wire inverter? If you've got a 120, 240 load, you know, does my load have a power factor that's going to be an issue? do I need to worry about those volt amps? Is it going to be big enough to support that load? And it does matter. I have in the past had loads, a couple of them that caused me issues. I had one that had was a telecommunications site that had a horrible power supply for the radio equipment that ended up giving me a power factor of about 0.5. So I had the load was, let's see, I think I had, the load was only supposed to be at 250 watts. We put a 200 or 250 watt inverter on there, but it wasn't working because with the power factor, really needed something that was 300 volt amps. And my 250 volt amp inverter wasn't going to support a load of 300 volt amps. So I had that problem once before. The other time I see is with some of these LED power supplies. Although your LED lights may be drawing a small amount of power, you might think that they're only, may have a 12 watt LED. The problem is these power supplies, these ballasts for them, some of these ones can be pretty bad actually, and they end up causing you these power factor issues, which means that it may end up being, again, if it's as bad as a 0.2, all of a sudden that 12 watt load is really consuming 60 volt amps. Now the other thing is that that's an inefficiency as well that causes an issue. So if you size your system, say based upon 12 watts, but you're really consuming 60 volt amps, that means your system is running inefficiently, and you may find your system, your standalone power system, failing because your load is inefficient. You don't realize it, but the inefficiency, it wasn't factored into your calculations, and all of a sudden you've got a load that is consuming 20, 30, 40, 50% more than it was designed for, and you're finding yourself shutting down in the wintertime. So something else to consider about this power factor. So it's important to understand that. Again, most loads aren't a problem because most of the manufacturers understand this, and they're going to put an extra capacitor or inductor, whatever it is, in there to compensate for that lag. If you've got your voltage lagging your current, you can put an inductor in there to slow the current down so it matches back up to the voltage. And the same thing on the other side. If you've got your current lagging your voltage, you put a capacitor in there to slow down the voltage, so then it catches back up to the current, or the current can catch up to the voltage at that point. So again, that's why you see a capacitor frequently on top of a motor. It's there to try to correct that problem. Okay, inverter, we talked about that before. It's just a device that changes direct current to AC current. And you'll notice the schematic symbol for that is, you'll notice the input to that is the sine for the DC. It's the solid line with the dashed lines underneath it, and you've it's a box with a slash through it, and you've got the sinusoidal wave on the output. And the same type of thing kind of happens on the DC-DC converter. It's a device that converts one DC voltage to another. And again, it's almost the same exact symbol as the inverter. It's the box with the line through the middle of it, and you've got the DC symbol on the input, which is the solid line with the dashed lines underneath it. You just notice it's having a sine wave on the other side, which is the output. It's going to be another DC symbol. So now let's talk a little bit about rectifiers versus power supplies versus battery chargers. Actually, Errol, how are we doing on time, and do we have any questions so far?
I think we're pretty good on time. No questions so far, so I think we can keep going.
Okay, otherwise I would table this stuff for EE1 or 2. But okay, so a rectifier basically is a device that converts the alternating current to DC current. So it's going to, there are two different types. Generally, they're just really simple. They're just diodes, essentially, as all they are. The half-wave rectifier is just a single diode, and the full-wave rectifier actually requires 4 diodes. It's also sometimes referred to as a bridge rectifier. Now, what that does is it takes that sine wave, and in the case of the half-wave, it just clips the bottom of that waveform off. Remember I told you you're going from a positive to a negative on the peak? Well, it just removes the negative, and all you have is positives now. In the case of the full wave, because you don't want to waste energy, basically you've wasted half your energy if you just if you just don't use that bottom half. It just, that's kind of a waste. So in a full wave rectifier, you pretty much take that bottom half of the wave and you flip it over, making it a positive. So now you're taking advantage of all of the energy, but you still have these humps. You still have a wave to it. It's not a flat line. And that's what a rectifier does. A rectifier basically just takes the the AC waves, and it just gets rid of the negative to it, just makes it a positive, whether it's, again, whether it's a full wave or a half wave. Now, if you were to take that and you were to put a filter on the output, basically you can knock these humps down and basically flatten it out and equalize it. That gives you a power supply. So what a power supply can do is, and again, this is kind of an example of a 9-volt one. You got your AC in, it goes through a transformer to knock it down a little bit to knock that voltage down, but still AC. You run it through that bridge diode, and again, there's your 4 diodes. That's your bridge diode. Then you run it through a bunch of capacitors, inductors, and stuff like that at your filtering circuit, and you get a nice constant 9-volt on the output. Okay, what's important to understand though here is that, again, so this is just, you add a filter on the output, but again, now this is not necessarily good for charging a battery because it is designed for a specific voltage out. It's not designed, it's designed for a continuous, consistent voltage. It's not designed to charge a battery, and it's not designed for the current so much as it is for the voltage, because again, the filter is to do just that. So, and talking the filters a little more here, the important thing here is that the filter removes that AC ripple, okay, and depending upon how good the filter is how much of the ripple is removed. If the ripple is still there, it may cause noise on some of your communications equipment or something like that. So if you have things that have a noise problem, you probably don't want the AC ripple on there. Now, if you're talking about a battery charger, batteries actually don't mind the ripple, and actually the ripple is actually good for the batteries. So you don't necessarily need to have a good filter for a battery charger. And again, this is kind of the things you have to start to think about. If you've got a load that requires a power supply and you're trying to put a battery on it, that may not be the right thing to do because that battery is not going to get properly charged. Might be great for the load, but not good for the battery. And vice versa, you have to be careful when using a battery charger only as your for your load. Perhaps you may not get a clean enough clean enough DC voltage for your load, as there might be a little ripple in there. Now, the nice thing about a battery is the battery kind of acts as a filter, actually, to be honest. It's got a giant capacitor in there with the plates. So sometimes the battery can actually help to filter that out, which is why a battery charger is what you should use for charging batteries. Now, there are some caveats there. Sometimes you can get away with using a power supply to charge a battery if it's done a certain way. And obviously, sometimes with the battery there, you can use your battery charger to support your load, again, with your battery on there, making certain you have things that are working correctly together. Okay, so, but again, the key here is the battery charger is not designed necessarily for the voltage, but it's designed to recharge the battery by putting current through it. Okay, so if you remember some of the webinars, I talk a lot about how it's important to get the amps into the batteries. That's why batteries are amp hours and how important the amps are. It kind of comes back to this again. It's important here in this case, the battery charger is about the amps, whereas a power supply is more about the voltage to the load. The other thing is the battery charger is going to have other things in it that are going to be good for trying to charge your battery, whether it be multi-stage. And we've talked about this a lot with the PV chargers, but it also applies to the AC ones as well. Whether you have a bulk charge, absorption time, and then a flow voltage, may also have an equalize with it. Okay, you've also got temperature compensation, which is also very important. We've covered that multiple times in other webinars. And it may have some other things too. It may have some advanced logic to it for lithium-ion batteries or other batteries. It may have some remote communications options, maybe even a generator starter or other features like having it be parallel series stackable. So again, just keep in mind that these are different devices that have different applications. You want to make certain that you're using the correct product for the application. And if anytime you have any questions about this stuff, please just contact us. We're happy to help you with trying to select the correct product for your application. So with that said, I think we have wrapped up our EE 101 talk, and we will again continue on with some of these things in the EE 102, and I hope that you've learned a lot here, and we're going to try to apply some more of these things again on our next webinar on basic system sizing. We're going to talk about how to apply some of these things to the load, a little bit more about that, how do you calculate the loads and things like that. In the meantime, we have a whole bunch of tech notes on our website. Please feel free to see those on go into detail on some of these options like understanding the loads and things like that. Also on some of the battery basics. And again, our webinars are also up there. Some of the previous ones we've done. And this will be up there as well within 24 hours.
All right.
Okay.
We do have a couple questions, Rob. The first question is a reference to voltage over hertz or voltage per hertz. I'm not sure if that was a specific reference or if that was a nomenclature issue, but somebody is wondering how that's used.
I am not really certain with that reference, but if you think of it in terms of units, the hertz is basically an inverse of time with regards to seconds. So what I would do is if I was trying to work with that, I would take the hertz and I would convert it to seconds and then work with it that way. And then what you can do is if you apply the voltage to that, I don't know what you would do with that. I'm not familiar with any units because power is with regards to current times voltage. It is with regards to time. Now, energy is with regards to time, but that's energy doesn't apply to the voltage. It applies to the power. So not certain how you would use those units, what it would be used for, but you could work it out that way. So you could come up with some type of volt-second unit. Again, I'm not certain what you would do with it or why you would need that or what that would be for, but I mean, you could work it out that way, which is, again, why the units can matter.
All right. Thanks, Rob. Appreciate the answer. If we get more clarification, I'll let you know. We do have a question about voltage regulation and that as a general topic. I'll let you discuss that, Rob. Maybe that's something that we include in the 102 webinar.
Yeah, I think we might get in that a little bit. I mean, I think that kind of comes back a little bit to, again, a power supply versus a battery charger. You can also think of it in terms of a DC-DC converter as well. What can happen here is that if you've got a load that has a tight window, that tight window may not work well for the batteries to get recharged, and you may need to add an additional device there, like a DC-DC converter. Frequently use DC-DC converters, not just because they may have multiple loads on a single system. You may have a 24-volt or a 12-volt load on the same system, and you have to convert from one voltage to the other. But sometimes we use it frequently because you may have a load that needs a regulated voltage, something with a tight tolerance, that can only handle, a very small range of maybe, plus or minus a tenth of a volt or something like that. And with working with batteries, we're going to need a bigger window than that. So I think we've mentioned that before in some of the other webinars with regards to loads and understanding loads. But that's just another good example, though, of if you've got a load that needs to have a tight regulated voltage in an off-grid system, you may need to have another device in there. And again, this is where using a power supply may be great for the load, but not good for the battery, because the battery needs to have a wider range for it to operate, and the load may want a very tight range. So you may need to add an additional device between the battery and the load to take care of that, like the DC-DC converter. That's one of the tasks that it has there.
Thanks, Rob. Appreciate it.
One more thing on that. Also be careful with these devices as well. Some converters might have a tighter tolerance than other ones. So some of them might be like plus or minus a volt. Some might be plus or minus a tenth of a volt. So just make certain that you're using the correct converter based upon your load requirements as well.
Good point. All right, we do have one more question, and that is about use of modified sine waves for appliances with transformers, like laptops. Rob, I'll let you speak to that.
That's a hit or miss thing. It really depends. Again, I'm just not a fan of using them at all. I just prefer to use a pure sine wave because I never know. Again, what happens sometimes is those transformers can actually heat up and get hotter than normal. They don't work as efficiently sometimes because they're looking for that smooth wave. When you're giving these coils and the transformer a square wave like that, it's not working as efficiently as it should. And then not to say it doesn't work, but it may not work optimally, and I don't know, maybe in the long run you could actually damage that by overheating it potentially. So again, it just depends upon the device and as to whether it is. I don't want to really kind of have a hard or fast rule on that because I've seen stuff work great on modified sine waves, no problem at all. I've seen other stuff that has been a problem, whether it be a noise issue or an overheating issue or something like that. So it can be hit or miss. You just don't know. It really depends on the load of the device. Again, so I don't want to have a hard or fast rule on that, but I will say this. If you got a pure sine wave, it's never an issue. You don't have to think about it.
All right, excellent answer. Thank you, Rob. That's all I have for questions right now. Give people maybe another few seconds if anybody has any last thoughts.
Okay, and while they're doing that, let's just plug our next webinars. Next month, and we're kind of, because of the holidays, we're not going to do too many here. We're trying to spread them out because everybody's busy with personal stuff and with business stuff, trying to get done before the end of the year. So we're going to repeat our basic standalone PV system sizing the first part of December. And then that's it until next year. Next year, we have a couple of them coming up. We're going to go into UPS sizing. So we're going to go from standalone PV sizing to sizing UPSs. And we've got actually have an online sizing tool for that. So we're going to demo that as well. And then later on in January, we're going to do the second part to this, EE1 to 2. We're going to get into the stuff in more detail. So we're going to get even, work on this and get into even more complicated things, building upon this. So
All right.
I guess if there are no other questions, we'll wrap it up. I know we're a little over time, so we'll go ahead and wrap it up here. Thank you for everybody for joining us. And if you do have other questions later, feel free to email us. Or call us, and we're happy to answer those. And again, look at our other webinars that we've already done, and as well as some of the other topics we have with regards to these things. And you might want to see how learning some of this information could apply to calculating your loads and things like that. So thank you, everybody, for joining us today. Have a good day, and hope to see you all again on another webinar coming up soon.
Thank you all.